If you haven't done so yet, please pause the video and try to solve the question on your own before listening on. Our goal, of course, is to calculate the electric field at a point midway between the two charges on the x-axis, so that would be a point located approximately right here. And in order to calculate the electric field there, we would want to consider the equation that we use when calculating the electric field produced by point charges, as we have in this scenario. And of course, that equation tells us that the electric field is equal to a constant times the magnitude of the charge divided by a distance squared. It's going to be useful to go ahead and label each charge, and so we can call this charge Q1, this one here Q2, and then the negative charge can be called Q3. And since there are three charges, we're going to have to make the calculation 3 times. So let's set up the equation 3 times. Now, in order to find the distance that we have marked R1, which would be the distance from the positive charge to the place that we marked X, we would have to use a little bit of trigonometry. So you can see that we have created a right triangle that's outlined in red here. Notice that this side of the right triangle is 0.5 meters, and so is this side, since it's an equilateral triangle. So we can use one of our trigonometric functions to find this side. Now, this side is opposite from the 60-degree angle, so maybe it's a good idea to use sine. And we know that the sine of 60 degrees would equal that opposite side, which we're calling R1, over the hypotenuse of this triangle, which is 0.5. So if we multiply both sides by 0.5, we'll be able to solve for R1. And when we do that, we can see that R1 is equal to approximately 0.433 meters. Now, R2 is going to be the distance from the positive charge to the place marked X. That's simply going to be half of the distance that's marked 0.5. So we know that R2 is going to be 0.25 meters. And then the same thing with R3, which is the distance from charge 3 to that X. That too will be half of the 0.5 meters. So we can confidently say that 0.25 meters is the R3. So with those distances, we're going to be able to get ready to plug in. Notice for the charges, they're given in nanocoulombs. So what we'll have to do is multiply each one of them by 10 to the negative 9 in order to put it into the standard unit of coulombs. So we'll do that for all three charges, and then K is a constant. So we'll just plug in all the known values now. So all the known values are plugged in. Notice that the charge Q3, even though it was negative in the diagram, we're just using a positive value for that charge because we took the absolute value. So now we'll pick up our calculators and process these three calculations. And so here are the three electric field magnitudes in red. What we must next do is consider the direction of these three electric fields. Let's first consider the electric field produced by charge 1. Notice that charge 1 is positive. We know that electric fields will point away from positive charges. So the electric field E1 will be pointing down in the negative y direction. Now consider the electric field produced by charge 2. Again, it points away from the positive charge, and in that case it would be pointing to the right. So E2 would be pointed to the right. And finally, consider the electric field produced by the negative charge. Electric fields produced by negative charges point towards the negative charge, so E3 would also be pointing to the right, just like E2. It's a little messy, but hopefully we can see those three vectors. Now, what we'll do is combine the E2 and E3 together since they're both pointing in the positive x direction. In other words, we can safely go ahead and add this electric field to this electric field to get the total electric field in the x direction. So here is that calculation. The total electric field in the y direction is simply the electric field marked E1. And so here is that electric field. So in essence, we have an electric field pointing in the x direction to the right, and then another electric field pointing in the y direction downward. What we need is the total or resultant electric field, which would be the hypotenuse of this right triangle. So we're going to use Pythagorean theorem now to find the magnitude of the hypotenuse of this triangle. So we've added the labels of the electric fields, and then to use the Pythagorean theorem, we could simply say that the x component squared plus the y component squared is going to equal the resultant squared. And then to solve for the resultant, we can just take the square root of both sides. And then we'll come down here to show the work. So when you take the square root of the x component squared plus the y component squared, you end up with this answer as your final magnitude of the electric field. To get the angle, which we can mark theta, we would take advantage of the opposite side of our right triangle, as well as the adjacent side of our right triangle. And of course, the trigonometric function that relates opposite to adjacent is the tangent function. So we're going to go ahead and say that the angle will be the inverse tangent of the y component divided by the x component. And so when we plug in the y and x component, we get negative 4.4 degrees for that angle. So the final answer can be summarized as follows. The total electric field will have a magnitude of 1.88 times 10 to the third newtons per coulomb, and then the angle will be 4.4 degrees below the x-axis. Notice it was below because of that negative sign in the angle. Thanks for taking the time to watch the video. If you liked it, please click the thumbs up icon and also subscribe to the channel so you can stay tuned for additional videos. Remember, you're welcome to send in your own question to this email address, and I'll do my best to answer it on YouTube.